Hi, I want to share with you something that I recently learned and found interesting. It is an introduction to trigonometry with some exciting applications. I hope you enjoy it. Trigonometry deals with the relationships of angles and sides in a triangle. If you have a right angle triangle with sides as shown, then for the angle theta, the side A is known as the base, side B is called the perpendicular, and C is the hypotenuse. These are the definitions of sine, cos, and tan of an angle. I have also added in cosec, sec, and cot that are related to them. So the sine of an angle is the length of the perpendicular divided by the length of the hypotenuse. Here is how you calculate the sine, cos, and tan of a few angles. Let's take an equilateral triangle of side 2, ABC. Drop a perpendicular line from the top of the triangle. Now the triangle ABD has angles 60, 30, and 90, which is what we need. Solve for the length of the perpendicular using Pythagoras' theorem. It will be the square root of 3. Using the term definitions on the previous slide, we get the following results. Notice what you have found and try seeing if you get the same answers with different side lengths for the equilateral triangle. If you did it correctly, you should. Continue looking at the results and see if you find some relationships between them. One of them would be that sine 30 is equal to cos 60 and cos 30 is equal to sine 60. Another thing you may have noticed is the identity that sine squared theta plus cos squared theta is equal to 1. This can be proved using Pythagoras' theorem, which is a squared plus b squared is equal to c squared. Dividing by c squared gives us the following equation. But we know that sine theta is a divided by c and cos theta is b divided by c. Hence the identity emerges that the square of the sine of an angle and the square of the cosine of the same angle add to 1. We have now used Pythagoras' theorem, but now let's prove it. There are hundreds of different proofs of Pythagoras' theorem. I have picked one of them to explain. The two pictures are the same apart from the 4 triangles being rearranged. In the first one, the green part is made up of a squared and b squared, and in the second one, the green part is made of c squared. There isn't much more to explain. Sine and cos of a plus b and a minus b. The above equations can be proved using geometry, but we won't go into proving them now. Here are the general equations to find sine, cos, and tan of any angle. Please note that in all of the equations above, all the thetas are in radians. A radian is another unit of measure for angles, like degrees. 2 pi radians is equal to 360 degrees, so 1 radian is approximately 57.3 degrees. When we used what we have learnt in trigonometry, imagine you wanted to estimate the circumference of the Earth. You dig a deep well somewhere near the equator. At noon, one day each year, the summer solstice, between June 20th and June 22nd, the sun's rays shine straight down into the hole, illuminating the water at the bottom. So the sun is directly overhead. On other days, the sun's rays hit the well's sides. You also have a tall pole, and you go to a place, north or south, a known distance away from the well, where the sun is never directly overhead. During summer solstice, you could observe the length of the shadow created by the pole. You know the pole's height as well. Below are 2 equations to find theta. Corresponding angles are equal, so theta is equal to y. Now that you know the angle y, and you know the length of the arc that subtends or makes the angle y, you can solve for the length of the arc that makes a full 360 degrees. This was first done in about 300 BC by Eratosthenes in Egypt, and he got a pretty accurate estimate. How would we find the distance to nearby stars? This can be done using a method called parallax. An example of parallax is observing nearby objects against a further background from each of your eyes. The nearer object would appear to be in a very slightly different position, as seen from each eye, in comparison to the background. Knowing the parallax angle a star moved relative to far-off stars, which appear fixed, and taking the size of the Earth's orbit around the Sun as the baseline, you can calculate the distance to the star. The position of the star changes more for a larger baseline, making it easier to observe. The nearer the star, the more the angle changes as well. One of the best baselines to use is the orbit of the Earth around the Sun. Even using this 186 million mile baseline for the nearest star, it would still be really hard to see the shift. The parallax angle for Proxima Centauri, the nearest star, is 0.77 arcseconds. An arcsecond is 1/3600th of a degree. So how do we find the distance to the star? Here's what we already know. We know the distance from Earth to the Sun, call it S. We measure the parallax angle A of the triangle shown. We want to know the distance to the star from the Sun, call it D. Here is the equation to find D. Because A is very small, tan of A by 2 is approximately equal to A by 2. Remember that this only works when the angle is in radians. Therefore, you can solve for D. The distance to Proxima Centauri is approximately equal to 4.3 light years.